At this very moment, while you absorb these words, an extraordinary phenomenon is unfolding within our solar system. Since the discovery of 3 Atlas in July, the celestial realm above us has grown increasingly enigmatic. From its first detection, this ancient voyager from beyond our stellar neighborhood has confounded the astronomical community. Yet its inexplicable chemical composition and emerald luminescence no longer represent its most perplexing attributes. The most bewildering aspect is the procession of objects trailing in its path. Our typically orderly cosmic vicinity has transformed into a congested thoroughfare of converging celestial bodies, exhibiting clustering behaviors that defy statistical probability. From a formation of 7 comets arriving in unison to a recent succession of asteroids sailing past our planet, the phenomena we're observing in the nocturnal heavens are decidedly abnormal. Astronomers now find themselves compelled to pose a fundamental question. What influence is 3 Atlas truly exerting upon our solar system? Join me on this nocturnal investigation as we determine whether we're experiencing the galaxy's most remarkable coincidence or something far more. Significant. Mid-September 2025 was anticipated to be uneventful, merely another period of standard cosmic activity, the variety that astronomers document with methodical efficiency before proceeding to subsequent observations. However, the cosmos had alternative intentions. What transpired during those clear autumn weeks was something altogether unexpected. A celestial procession materialized that sent researchers rushing to their observational instruments and left the general public questioning whether we were witnessing something beyond simple happenstance. The principal attraction made its appearance initially. Asteroid 2025 FA22, a mountain-proportioned fragment of stone measuring approximately 130 to 290 meters in diameter. On the 18th of September, it traversed past Earth at slightly more than 2 lunar distances, approximately 835,000 kilometers distant, sufficiently proximate to generate public attention, adequately remote to permit restful sleep. Yet here's where the narrative becomes compelling. FA22 didn't arrive in isolation. This wasn't the conventional solitary asteroid making its anticipated passage. Rather, it resembled the inaugural performance at a cosmic amphitheater with numerous performers ascending the platform in quick succession. The smaller near-Earth object 2025 Ray J2 had already completed its entrance 3 days prior on the 15th of September, streaking past at merely 0.78 lunar distances, a scant 300,000 kilometers from our threshold. In cosmic measurements, that's essentially within arm's reach. However, these weren't separate occurrences. Throughout that identical week, dozens of supplementary sublunar distance visitors traced their paths across our local sector, each one documented and monitored by the worldwide network of space observation systems. It constituted routine traffic, according to the statistics. Nevertheless, something about the concentration felt unusual. The synchronization appeared nearly orchestrated, as though these primordial wanderers had synchronized their arrivals for optimal theatrical impact. Subsequently arrived the accompanying performers. Comet C2025R2, identified by the Swan instrument aboard the Soho spacecraft on the 11th of September, commenced brightening toward visibility with the unaided eye near the Virgo constellation. Its appendage extended across the twilight sky like a cosmic brushstroke, observable to anyone aware of the proper viewing location as dusk yielded to complete darkness. The comet's ultimate fate following perihelion remained ambiguous. Numerous such objects disintegrate under the sun's extreme thermal energy, leaving behind merely luminous debris pathways as testaments to their transient stellar existence. Meanwhile, present in the background of every astronomical news bulletin was another recognizable presence, Apophis, officially classified as 99,942 Apophis. This represents the asteroid that once dominated every planetary protection concern registry. The 400-meter-wide Rocky Mountains scheduled for an unsettlingly close interaction with Earth on the 13th of April, 2029. That transit will transport Apophis within 32,000 kilometers of our planet's exterior, nearer than our geostationary communication satellites, sufficiently close to observe with unassisted vision as it races across the night sky at 50,000 kilometers per hour. Yet, the genuine centerpiece of this celestial performance was still awaiting its moment. Concealed among the standard discovery bulletins was something without precedent. 3I Atlas, alternatively designated C2025N1, identified on the 1st of July, 2025 by the Atlas Survey team in Chile. This object distinguished itself from everything else occupying our telescopes that September. It wasn't simply another asteroid or comet from our local solar system family. This was something considerably more remarkable. An interstellar visitor, merely the third ever authenticated, transporting chemical indicators that would challenge everything we presume to understand about planetary formation the Atlas team had originally detected. It is merely another indistinct point advancing against the star field. However, as subsequent observations refined its trajectory, the mathematics revealed an exceptional narrative. This object was navigating on a hyperbolic orbit, signifying it possessed more than adequate velocity to escape our sun's gravitational hold completely. It had originated from elsewhere, another stellar system, potentially light years removed, and following its brief interaction with our solar neighborhood, it would proceed onward into the cosmic darkness, never to return. What rendered 3I Atlas even more exceptional was its chronology. Perihelion was projected for late October 2025, merely weeks following the September asteroid precession. Subsequently, like a performer departing stage left, it would disappear into the solar brilliance, obscured by our star's overpowering radiance. However, patience would yield rewards. In early December, as Earth's orbital progression transported us to a superior viewing perspective, 3I Atlas would resurface from behind the sun's veil, presenting telescopes their optimal opportunity to examine an authentic specimen of interstellar territory. The observation window was flawless. Excessively flawless, some might contend. At nearest approach in December, the object would remain 1.88 astronomical units distant, approximately 270 million kilometers from Earth, sufficiently remote to present zero hazard, adequately proximate for comprehensive spectroscopic examination by our most sophisticated instruments. It was as though the universe had provided a meticulously packaged specimen from another stellar system, delivered directly to our astronomical threshold, complete with ideal viewing circumstances and an unhurried schedule for investigation. But why at this moment? Why this abrupt increase of cosmic activity clustering around the identical few weeks? Enhanced surveys certainly contributed. Hera C. Rubin Observatory had recently captured its inaugural light images in June 2025, acquiring thousands of new asteroid detections in approximately 10 hours of functioning. More observational capacity was examining the sky with greater sensitivity than ever previously, exposing the authentic population density of our solar system's small body constituency. Nevertheless, the chronology felt excessively convenient, excessively coordinated to dismiss as simple observational predisposition. Was there something exceptional about September 2025? Some gravitational convergence or seasonal orientation that had attracted these objects into confluence? Or were we experiencing the initial act of something more substantial? A cosmic spectacle unfolding on temporal scales far exceeding human comprehension? The atmosphere among astronomers wasn't apprehension, but pressing inquisitiveness. Planetary protection systems had advanced considerably since the era when impacts were exclusively the domain of catastrophe films. We now possess the technological capacity to track, characterize, and even redirect potentially dangerous objects. The recent accomplishment of NASA's DART mission had demonstrated that kinetic impactors could successfully modify an asteroid's path, while the European Space Agency's Hera mission was en route to forensically investigate the outcomes. However, knowledge and readiness were only as effective as the warning duration they supplied, and that generated uncomfortable inquiries about the visitors we hadn't detected yet, those still approaching from the sun's direction, concealed in the glare until their final approach. If FA-22 had been on an impact trajectory instead of a secure flyby, would we have possessed sufficient advance notification to deploy an effective countermeasure? And what did 3I Atlas, with its alien chemistry and interstellar origins, communicate to us about the unobserved population of objects drifting between the stars? The September increase had awakened something within the collective scientific awareness. It wasn't alarm. It was the acknowledgement that our solar system was far more dynamic, far more interconnected to the broader galaxy than we had previously conceived. We were observing the opening scene of humanity's evolution from a single planet, species to active contributors in galactic-scale phenomena. However, initially, we needed to comprehend what we were actually confronting. If FO-22 had struck Earth instead of passing safely by, what would that collision have resembled? The physics of cosmic collision are merciless. When asteroid 2025 FA-22 traversed past, Earth on the 18th of September had a distance of 835,000 kilometers. It carried with it a kinetic energy equivalent of approximately 100 megatons of TNT. To place that in context, that's roughly 2,000 times more potent than the explosive device that devastated Hiroshima, all concentrated in a single rocky projectile, measuring between 130 and 290 meters. Across. Yet energy constitutes only a portion of the narrative. What matters predominantly is how that energy becomes delivered to our planet's surface. And that depends entirely on an intricate interaction of physics involving atmospheric penetration angle, object composition, and sheer cosmic fortune. The distinction between a regional catastrophe and a global extinction occurrence often reduces to factors as elementary as whether the approaching object is composed of solid iron or loose aggregate, whether it arrives at a precipitous angle or grazes the atmosphere, and whether it detonates in the air or penetrates through to the ground. FA-22's approach velocity of approximately 10.8 kilometers per second was characteristic for near-Earth objects, sufficiently rapid to compress and heat the atmosphere, preceding it into a plasma envelope, but not so extreme as to suggest an origin from the outer solar system or beyond. At that velocity, atmospheric penetration would have been spectacularly violent. The object would have commenced glowing like a secondary sun while still hundreds of kilometers above the surface, its leading edge reaching temperatures of several thousand degrees as it plowed through progressively dense atmospheric layers. For a stony asteroid in FA-22 size category, the most probable scenario would have been an airburst, a complete atmospheric detonation occurring somewhere between 5 and 15 kilometers above the surface. This is what occurred at Tunguska, Siberia, in 1908, when an estimated 3 to 15 megaton airburst leveled over 2,000 square kilometers of forest without ever producing a crater. The FA-22 scenario would have been substantially more powerful. Envision standing 200 kilometers away from ground zero on a clear morning. Initially would arrive the illumination, a flash more brilliant than the sun, visible even in broad daylight, searing retinas and igniting clothing and vegetation across hundreds of square kilometers. The thermal pulse would persist several seconds, sufficiently prolonged to produce third-degree burns to exposed skin at distances surpassing 100 kilometers. Subsequently would arrive the sound. The shock wave from a 100 megaton airburst would shatter windows across an area, the dimensions of a small nation. The overpressure wave would flatten most residential structures within 50 kilometers of ground zero and cause significant structural damage out to distances approaching 150 kilometers. Even well-constructed concrete structures would endure severe damage within the inner destruction zone. But what if FA-22 had been composed of denser material or arrived at a shallower angle that permitted it to penetrate deeper into the atmosphere before fragmenting? The crater scenario presents an entirely different category of devastation. Utilizing established impact modeling programs like Impact Earth, we can estimate that a 200-meter iron asteroid striking at 10 kilometers per second would excavate a crater approximately 3 kilometers in diameter and 500 meters deep. The immediate effects would be apocalyptic for anyone within visual range. The impact would vaporize the asteroid and an equivalent mass of target rock, launching millions of tons of superheated debris on ballistic trajectories that would rain burning material across thousands of square kilometers. The seismic shock would register as a magnitude 6.5 earthquake, collapsing buildings and triggering landslides across a region hundreds of kilometers wide. Yet, perhaps the most terrifying scenario would be an ocean impact. Over 70% of Earth's surface is covered by water, rendering this statistically the most likely outcome for any randomly arriving asteroid. When cosmic projectiles strike the ocean, they don't simply disappear into the depths with a large splash. They generate something far more hazardous: tsunamis. The physics of impact-generated tsunamis are still being refined by researchers. But recent modeling suggests that even a 250-meter asteroid striking deep ocean would produce initial wave heights exceeding 100 meters at the impact site. These waves would propagate outward at jet aircraft speeds, carrying sufficient energy to remain dangerous across entire ocean basins. An FA-22-sized impact in the mid-Atlantic could potentially send 10-meter waves crashing into coastal cities from Boston to Barcelona within hours of impact. However, there's an important qualification that often becomes lost in disaster scenarios. Wave height attenuates with distance. Classic hydrocode simulations demonstrate that tsunami waves lose energy as they travel, with typical height reductions following predictable mathematical patterns. A devastating 100-meter wave at the impact site might be reduced to 10 meters by the time it travels 60 kilometers and continue diminishing as it crosses ocean basins. The devil, as always, resides in the details of coastal geography and local BATHYMETRY. The regional versus global impact question is essential for understanding the genuine threat posed by city-killer-sized asteroids. An FA-22 impact would certainly cause regional devastation, potentially affecting millions of individuals, but it would be unlikely to trigger global climate effects or threaten human civilization as a whole. That level of destruction requires substantially larger impactors, objects in the kilometer-plus size range that strike perhaps once every few 100,000 years. For comparison, consider the Chelyabinsk event of February 15, 2013. That 20-meter asteroid created an airburst equivalent to approximately 500 kilotons of TNT, injured over 1,500 people, primarily through flying glass from shattered windows, and provided the world with dramatic dashcam footage of what occurs when cosmic debris meets modern civilization. The Chelyabinsk object was roughly 1/10 the diameter of FA-22, highlighting just how rapidly impact energy scales with size. What rendered Chelyabinsk particularly concerning for Planetary defense experts wasn't the damage it caused, but the fact that it arrived completely undetected. The asteroid approached from the direction of the sun, hidden in the solar glare until the final moments before atmospheric entry. No telescope on Earth detected it coming. This represents one of the fundamental Blind spots in our current detection network. The Sun Ward. Approach corridor where even city killer-sized objects can arrive with essentially zero warning. FA-22s. Safe Flyby actually provided valuable real-world experience for international planetary defense coordination. The asteroid's brief appearance on the European Space Agency's risk assessment list, followed by its removal after additional observations refined the orbit, gave agencies practice in the delicate art of public communication about potentially hazardous objects. How do you inform the public about a possible threat without causing panic? How do you coordinate international response efforts when dealing with objects that could affect multiple countries? The International Asteroid Warning Network conducted what amounted to a live-fire exercise during FA-22's approach, testing communication protocols and observation coordination procedures that would be essential in a genuine emergency. The fact that it was ultimately a false alarm didn't diminish the value of the rehearsal experience. In fact, it provided something even more valuable, proof that the system could function under pressure. But the exercise also highlighted critical gaps that remain in our planetary defense capabilities. Lead time is everything when it comes to asteroid deflection. The earlier we detect a potentially hazardous object, the smaller the deflection required to safely alter its trajectory. A gentle nudge applied years in advance can eliminate the need for desperate last-minute measures. Current deflection technologies, validated by NASA's successful DART mission, rely primarily on kinetic impact, essentially playing cosmic billiards with asteroids using high-speed spacecraft. The technique functions, but it requires precise knowledge of the target's composition, structure, and rotation state. A rubble pile asteroid responds very differently to impact than a solid iron mountain, and obtaining those calculations incorrectly could mean the difference between successful deflection and catastrophic fragmentation. The FA-22 scenario serves as a sobering reminder that we inhabit a planet embedded in a shooting gallery of cosmic debris. Most of it is harmless sand grain-sized particles that burn up harmlessly in our atmosphere as meteor showers. But occasionally, something larger slips through the gaps in our detection network. And when it does, the consequences can be devastating on scales ranging from city blocks to entire civilizations. The encouraging news is that we're improving at this cosmic neighborhood watch. New survey telescopes are becoming operational with unprecedented capability to detect and track potentially hazardous objects, while space-based infrared observatories will soon close the Sun Ward detection gap that allowed Chelyabinsk to arrive unannounced. Yet, as we've become more proficient at cataloging the threats in our immediate solar system neighborhood, we've also begun to realize just how much we still don't comprehend about the larger cosmic environment. Objects like 3I Atlas remind us that our solar system is not an isolated island, but rather a rest stop along the galactic highway, constantly receiving visitors from the vast spaces between stars. Which raises an intriguing question about the September surge. Were we witnessing a random clustering of unrelated objects? Or could there be deeper connections between FA-22, the other near-Earth asteroids, and the mysterious interstellar visitor that dominated astronomical headlines? Before we can answer that question, we need to understand what else was sharing the cosmic stage during those remarkable autumn weeks. While asteroid FA-22 captured headlines with its close approach, another celestial performer was quietly preparing for its debut in the evening sky. Comet C2025R2, discovered by the Solar Wind Anisotropies instrument aboard the SOHO spacecraft on September 11th, was rapidly brightening toward naked-eye visibility as it fell inward toward the Sun's position. Unlike the predictable, well-mapped trajectory of FA-22, this comet represented something far more volatile and unpredictable. Swan's discovery of the comet highlighted one of the most elegant aspects of modern space-based astronomy: The instrument wasn't designed to hunt comets. Its primary mission involves mapping hydrogen emissions from solar-wind interactions at the edge of our solar system. But it turns out that when comets begin their final approach toward the Sun, they start releasing hydrogen-rich water vapor in quantities detectable from millions of kilometers away. Swan essentially stumbles across new comets by watching for their hydrogen signatures erupting against the background of interplanetary space. By mid-September, C2025R2 had brightened to approximately sixth magnitude, hovering right at the threshold of naked-eye visibility under dark rural skies. Amateur astronomers began reporting sightings near the constellation Virgo, close to the bright star Spica, and the reddish glow of Mars in the western sky after sunset. The comet's tail was growing longer and more structured as solar heating drove volatile ices to sublimate from its nucleus, creating the classic coma and tail structure that has inspired human imagination for millennia. But comets are notoriously fragile creatures. Unlike the solid rock and metal construction of asteroids, comets are essentially dirty snowballs, loose aggregations of ice, dust, and organic compounds held together by weak gravitational forces and frozen volatiles. As they approach the Sun, the same heating that creates their spectacular tails can also tear them apart entirely. Many comets discovered by Swan never survived their first close encounter with solar radiation, fragmenting into debris streams that produce brief meteor showers before dissipating entirely. The physics behind comet activation involves a complex interplay of sublimation temperatures and solar heating. Water ice begins sublimating at temperatures around 200 Kelvin, while more volatile compounds like carbon dioxide and methane begin outgassing at even greater distances from the Sun's position. As these materials transition directly from solid to vapor, they create jets of gas that can dramatically alter a comet's trajectory through non-gravitational forces. This makes comet orbits notoriously difficult to predict with high precision, especially for objects making their first approach from the distant Oort cloud. C2025R2's survival prospects remained uncertain throughout September. Fresh comets from the outer solar system often contain pristine ices that have never been exposed to significant solar heating. When they finally encounter the Sun's radiation, the rapid sublimation can create internal stresses that exceed the comet's structural integrity. The nucleus might split into multiple fragments, each creating its own tail and coma, or it might disintegrate entirely into an expanding cloud of debris. Yet, even as this new comet commanded attention from amateur observers, another cosmic celebrity was preparing for its own moment in the spotlight. Asteroid 99,942 Apophis, the 400-meter-wide mountain of rock that once topped every planetary defense worry list, continues its inexorable approach toward the closest asteroid encounter in recorded human history. On April 13th, 2029, Apophis will sweep past Earth at a distance of just 32,000 kilometers, closer than our geostationary communication satellites, close enough to appear as a bright, fast-moving star, visible to the naked eye, even from urban locations. The flyby will occur at approximately 50,000 kilometers per hour, meaning observers will be able to watch the asteroid's motion against the starfield in real time without telescopes. What makes the Apophis encounter scientifically fascinating is that we know with absolute certainty it poses no impact risk for at least the next century. Radar observations and optical tracking have refined its orbit to extraordinary precision, eliminating any possibility of collision during the 2029 flyby or for decades afterward. This allows scientists to focus entirely on the remarkable opportunity to study a large asteroid during an extremely close approach. The gravitational effects of Earth's pull during the flyby will be profound and permanent. Apophis will experience tidal forces strong enough to alter its rotation rate, modify its surface features, and potentially trigger landslides or regolith redistribution across its entire surface. The asteroid that emerges from the encounter will be measurably different from the one that approached, providing a natural laboratory for studying how close planetary encounters reshape small bodies over geological time. NASA's OSIRIS-APEX mission, a repurposed version of the successful OSIRIS-REx sample return spacecraft, is already en route to rendezvous with Apophis shortly after the 2029 flyby. The spacecraft will spend months mapping the asteroid's post-encounter surface, measuring how the gravitational interaction with Earth has altered its physical properties and internal structure. This data will be invaluable for future asteroid deflection missions, which must account for how target objects respond to external forces. The timing of Apophis's approach, coming just 3.5 years after the September 2025 surge, raises intriguing questions about whether we're entering a period of increased near-Earth object activity. Statistically speaking, close asteroid approaches follow no particular schedule. They're essentially random events governed by the complex gravitational interactions that shape the solar system over billions of years. Yet the clustering of significant encounters within such a short time frame seems to challenge the notion of purely random distribution. Part of this apparent increase stems from observational bias. The completion of major asteroid surveys like LINEAR, NEAT, and Spacewatch over the past 2 decades has dramatically improved our ability to detect and track potentially hazardous objects. A Vera C. Rubin Observatory, which captured its first light images in June 2025, represents another quantum leap in survey capability. Its enormous field of view and sensitive detectors will rescue the entire accessible sky every few nights, providing unprecedented cadence for discovering new objects and monitoring known ones. But improved detection capabilities alone don't explain the September surge or the remarkable diversity of objects involved. Alongside FA-22's close approach and C2025R2's brightening display, dozens of smaller near-Earth objects threaded their way through our local cosmic neighborhood. Object 2025RJ2 passed at just 0.78 lunar distances on September 15th. Multiple sublunar distance encounters occurred throughout the month, each one cataloged and tracked by the Global Space Surveillance Network. The seasonal timing might offer clues about the underlying dynamics. Earth's orbital motion carries us through different regions of the inner solar system throughout the year, and it's possible that September 2025 corresponded to our passage through a particularly populated zone of space debris. Alternatively, the apparent clustering might result from the complex gravitational resonances that can synchronize the orbits of multiple objects over geological time scales. Comets add another layer of complexity to this cosmic choreography. Unlike asteroids, which follow relatively stable and predictable orbits, comets can experience dramatic changes in trajectory due to outgassing forces and gravitational perturbations from the giant planets. Long-period comets from the Oort cloud arrive with essentially no advanced warning, following orbits that haven't brought them into the inner solar system for thousands or millions of years. The distinction between asteroids, comets, and meteors often confuses public discussions of planetary defense. Yet these differences are crucial for understanding impact risks and mitigation strategies. Asteroids are essentially rocky or metallic mountains in space, following well-defined orbits that change slowly over time. Comets are volatile-rich objects, whose behavior can be unpredictable due to outgassing effects. Meteors are simply the visible light phenomena created when small particles burn up in Earth's atmosphere, regardless of whether their parent body was an asteroid or comet. This diversity of small body types reflects the complex history of our solar system's formation and evolution. The asteroid belt between Mars and Jupiter contains remnants of planetary formation that never successfully assembled into a planet, while comets preserve samples of the primitive ices and organics from the outer reaches of the early solar nebula. Each population tells part of the story of how worlds form around stars. And each presents different challenges for planetary defense. As autumn 2025 progressed, the cosmic stage was set for even more remarkable revelations. The September surge of familiar solar system objects was about to be overshadowed by something unprecedented, a visitor from another star system entirely, carrying chemical signatures that would challenge fundamental assumptions about planetary formation and the nature of interstellar space. But first, this mysterious traveler would have to navigate the complex gravitational environment of our inner solar system while remaining hidden behind the solar glare during its closest approach to the sun's location. When it finally emerged into telescopic view in early December, 3I Atlas would prove to be unlike anything astronomers had ever seen before. On July 1st, 2025, a routine automated sky survey captured something extraordinary disguised as an unremarkable dot of light. The Atlas telescope array at Rio Hurtado, Chile, had photographed thousands of such objects, asteroids, comets, and distant stars shifting position against the stellar background. But this particular dot would soon rewrite our understanding of what travels between the stars. Initially catalogued as just another potential near-Earth object, the object that would become known as 3I Atlas appeared different from countless other discoveries in the Atlas database. The automated systems flagged it for follow-up observations based on its apparent motion across the sky, and within days, telescopes around the world were tracking its trajectory with increasing precision. It was during this routine astrometric follow-up that astronomers realized they were dealing with something unprecedented. The mathematics were unmistakable. As more observational data refined the object's orbital elements, one parameter stood out with startling clarity. Its orbital eccentricity exceeded unity. In celestial mechanics, this is the signature of a hyperbolic trajectory, an orbit carrying more than enough velocity to escape the sun's gravitational influence entirely. This object wasn't bound to our solar system. It was just passing through. 3I Atlas became only the third confirmed interstellar visitor in human history, following the mysterious cigar-shaped object 1, Oumuamua, in 2017, and Comet 2I Borisov in 2019. But unlike those previous visitors, 3I Atlas arrived with perfect timing for extensive observation. Its trajectory would carry it to perihelion closest approach to the Sun on approximately October 30th, 2025, followed by its closest approach to Earth in December at a distance of roughly 1.8 astronomical units. That December distance translates to approximately 270 million kilometers, far enough to pose absolutely zero threat to Earth, but close enough for detailed spectroscopic analysis by our most powerful telescopes. It was as if the cosmos had arranged a cosmic delivery service, dropping off a pristine sample from another star system with optimal viewing conditions and plenty of advance notice. But the object's trajectory was only the beginning of its mysteries. As observational data accumulated throughout the summer and early autumn of 2025, 3I Atlas began displaying characteristics that challenged assumptions about both interstellar space and comet behavior. Size estimates from Hubble Space Telescope observations suggested an upper limit of approximately 5.6 kilometers for the nucleus, though the actual size was likely significantly smaller. This placed it in the intermediate range between typical comet nuclei and small asteroids. What truly set 3I Atlas apart from its interstellar predecessors was its unmistakably cometary behavior. Unlike 1I Oumuamua, which showed no visible coma or tail despite its puzzling non-gravitational acceleration, 3I Atlas developed a classic cometary appearance as it approached the sun's position. By September, ground-based telescopes were resolving a substantial coma d'Agi cloud of dust and gas surrounding the nucleus along with the beginnings of what would become an impressive tail structure. This cometary activity provided the first clues to the object's truly alien chemistry. When the James Webb Space Telescope turned its infrared spectrographs toward 3I Atlas in late summer 2025, the results were unlike anything seen in solar system comets. The object's coma showed an unusually high ratio of carbon dioxide to water vapor, among the highest CO to HO ratios ever measured in a comet dot. To understand why this chemistry is so significant, consider how comets form in typical planetary systems. Water ice condenses from the protoplanetary nebula at temperatures around 150 Kelvin, corresponding to orbital distances of approximately 2 to 3 astronomical units from a sun-like star. Carbon dioxide, with its lower sublimation temperature, condenses much farther out, beyond the snow line where temperatures drop below 78 Kelvin. The extreme CO dominance in 3I Atlas suggests formation in the frigid outer regions of its parent planetary system, far beyond where most solar system comets originate. Either this object condensed from a protoplanetary disk that was unusually rich in carbon dioxide, or it formed so far from its parent star that water ice never had a chance to accumulate in significant quantities. But the chemical anomalies didn't stop with carbon dioxide. Spectroscopic observations from the Very Large Telescope in Chile revealed another puzzling feature: prominent nickel emission lines with surprisingly weak iron signatures. In typical solar system comets, iron and nickel occur in roughly solar proportions, reflecting the composition of the stellar nebula from which they condensed. The apparent depletion of iron relative to nickel in 3I Atlas hints at chemical processing or formation conditions, unlike anything in our local cosmic neighborhood. As autumn progressed and 3I Atlas continued its approach toward perihelion, its tail structure became increasingly complex and visually spectacular. The Gemini Observatory and other ground-based facilities documented multiple tail components with different orientations and compositions, suggesting ongoing activation of volatile materials across different regions of the nucleus. The object was literally coming alive under solar, heating after potentially billions of years in the cold. Emptiness between stars. The timeline for observing 3I Atlas presented both opportunities and challenges. As it approached perihelion in late October, the comet would become increasingly difficult to observe from Earth due to its proximity to the sun in our sky. Solar glare would effectively hide the object during its most active phase, when thermal processing might reveal additional clues about its composition and internal structure, but patience would be rewarded. Earth's orbital motion would gradually improve the viewing geometry throughout November, and by early December, 3I Atlas would emerge from behind the solar glare into prime observing position. At closest approach to Earth in mid-December, the object would still be nearly 200 times farther away than the Moon, but well positioned for extended spectroscopic campaigns by major observatories. The intervening months of hidden observation presented a tantalizing mystery. What changes would occur as 3I Atlas reached peak solar heating? Would its unusual chemistry remain stable, or would the intense radiation drive off surface materials to reveal different compositions beneath? Most importantly, would the object survive perihelion intact, or would thermal stresses fragment it into multiple pieces like so many comets before it? Preliminary kinematic modeling suggested that 3I Atlas might be extraordinarily old, possibly more than 7 billion years, if recent calculations linking it to the galaxy's thick disk population proved correct. This would make it older than our entire solar system, a wanderer that had been drifting through interstellar space since before Earth existed. The chemical signatures preserved in its ices and rocky components could provide direct samples of conditions in the early galaxy when star formation rates and heavy element abundances were dramatically different from today. Unlike 1I Almuom's Brief visit and rapid departure. 3i Atlas offered the prospect of extended study across multiple observing seasons. Its moderate approach velocity and favorable geometry would keep it within range of major telescopes well into 2026, providing unprecedented opportunity to characterize an authentic piece of another star system. But even as astronomers prepared for months of detailed observations, nagging questions remained about the object's origins and journey to our solar system. How long had it been wandering in interstellar space? What star system had ejected it? And what were the circumstances of its appearance? Most fascinating of all, did its emergence during the same time frame as the September asteroid wave represent mere chance? Or might there exist deeper links between the interstellar traveler and the peculiar concentration of near-Earth object passages? The seeming coordination of these celestial occurrences was starting to challenge believability. Initially, the sequence of closely approaching asteroids appeared, followed by the brightening comet, and ultimately the appearance of an interstellar visitor bearing chemical signatures never before documented. Either we were observing an extraordinarily improbable convergence of disconnected events, or something more fundamental was directing this cosmic spectacle. While 3 Atlas pursued its trajectory toward perihelion, concealed by the intensifying solar brightness, astronomers could merely theorize about what discoveries would accompany its December reappearance. Yet the object had already started disclosing mysteries that would transform our comprehension of planetary origins, interstellar chemistry, and humanity's position in the galactic community. The inquiry had shifted from whether this visitor would yield fresh insights into the cosmos. The question became whether humanity was ready for the ramifications of what it might disclose about the universe, extending beyond our solar system's boundaries. The genuine enigma, however, was just starting to develop. Because while 3i Atlas commanded scientific focus with its extraterrestrial chemistry and primordial origins, an increasing number of investigators were beginning to recognize patterns in the September wave that implied something beyond random cosmic happenstance was operating. The September 2025 wave functioned as an unsettling reminder of precisely how vulnerable our planetary defense systems remain. Notwithstanding decades of technological progress and international collaboration, though we successfully monitored and analyzed every substantial object that neared Earth throughout those remarkable weeks, the concentration of passages underscored critical vulnerabilities that could prove devastating if occupied by the incorrect type of visitor at the incorrect moment. Examine the essential challenge of detection geometry. The overwhelming majority of our asteroid hunting telescopes constitute ground-based installations that can exclusively observe objects when they maintain sufficient separation from the Sun in our celestial sphere. This generates a substantial blind zone in the direction of our closest star, exactly the approach path that transported the Chelyabinsk impactor entirely undetected in 2013. An asteroid approaching from the sunward trajectory remains essentially invisible until the final hours or moments before atmospheric penetration. FA-22's trajectory fortunately transported it well outside of this detection shadow, permitting telescopes globally to monitor its approach for weeks preceding closest passage. However, if its orbit had possessed different inclination, or if its approach vector had aligned more precisely with the Sun-Earth axis, we might have possessed merely days or hours of advance notice instead of the sufficient lead time that enabled comprehensive characterization and public announcement. This sunward blind zone constitutes one of the most substantial weaknesses in our present planetary defense framework. Ground-based surveys have achieved notable advancement in cataloging near-Earth objects, yet they remain intrinsically constrained by the principles of optics and orbital mechanics. One cannot observe what remains hidden behind the most luminous object in the sky, regardless of telescope sophistication. The resolution requires relocating detection systems into space, where they can function independently of Earth's day-night cycle and atmospheric disruption. NASA's Near-Earth Object Surveyor mission, scheduled for deployment in September 2027, will position an infrared space telescope specifically engineered to detect asteroids from a location trailing Earth in our solar orbit. From this vantage point, NEO-Surveyor will possess the capability to identify objects approaching from directions that remain invisible to ground-based observatories. However, space-based detection represents merely the initial phase in a sophisticated sequence of planetary defense capabilities. After a potentially hazardous object is discovered, it must be characterized with adequate precision to evaluate the genuine threat level and establish the most effective response approach. This demands rapid follow-up observations from multiple installations, accurate orbit determination, and thorough analysis of the object's physical characteristics. The Vera C. Rubin Observatory, which acquired its initial light images in June 2025, constitutes a revolutionary advancement in this follow-up capacity. Its massive mirror and wide-field camera can resurvey the entire accessible sky every 3 nights, delivering unprecedented frequency for monitoring newly discovered objects and observing their orbital development. During its initial 10 hours of operation, Rubin identified thousands of new asteroid detections, showcasing the instrument's potential to substantially expand our census of the near-Earth object population. Nevertheless, detection and monitoring prove meaningless without the capability to actually respond to approaching threats. This is where NASA's Double Asteroid Redirection test mission has supplied invaluable real-world confirmation of kinetic deflection technology. The DART spacecraft's collision with asteroid Dimorphos on September 26, 2022, successfully modified the small asteroid's orbital period by 32 minutes, far surpassing the minimum 73-second alteration required to validate mission success. More significantly, comprehensive analysis of the impact disclosed that the momentum transfer efficiency, designated as beta, approximated 3.6, signifying the impact was nearly 4 times more effective than would be anticipated by simple momentum conservation. This amplification factor results from the expulsion of debris following impact, which functions like rocket exhaust to magnify the deflection effect. Comprehending this physics proves essential for designing future deflection missions. The European Space Agency's Hera mission, presently en route to the Didymos system, will arrive in 2026 to perform forensic examination of the DART impact location. Hera's comprehensive mapping and measurement of the crater and debris field will supply ground truth data for impact models, helping refine our understanding of how various asteroid types respond to kinetic deflection attempts. Yet kinetic impact represents just one instrument in the planetary defense arsenal. For larger objects or scenarios demanding more precise trajectory modifications, alternative techniques might demonstrate greater effectiveness. Gravity tractor spacecraft that employ their own gravitational field to gently pull asteroids off-course accumulate velocity changes over years or decades. Nuclear standoff devices could vaporize surface material to generate powerful rocket-like thrust. Ion beam shepherds could utilize focused particle beams to progressively ablate one side of an asteroid, producing continuous low-level thrust across extended periods. The crucial insight from planetary defense research indicates that all these techniques demand substantial advance time to prove effective. A gentle nudge administered years or decades beforehand can eliminate the necessity for desperate last-minute interventions. This explains why early detection proves so critical, not because we require time to evacuate cities or construct underground shelters, but because gentle deflection becomes exponentially easier with advanced warning. The International Asteroid Warning Network, established to coordinate global response to potential impact threats, performed what essentially constituted a live exercise during FA-22's approach. The asteroid's brief inclusion on the European Space Agency's risk assessment list, followed by its removal after supplementary observations, furnished valuable experience in the delicate balance between public notification and panic prevention. How does one inform the world about a possible asteroid threat without generating economic chaos or social disruption? How does one coordinate international response efforts when addressing objects that could affect multiple nations? These questions possess no simple answers, yet FA-22's flyby provided a relatively low-stakes opportunity to evaluate communication protocols and decision-making processes. The exercise disclosed both strengths and weaknesses in our current methodology. The swift international sharing of observational data permitted quick refinement of FA-22's orbit and prompt removal from risk assessment lists once the threat was eliminated. However, public communication remained inconsistent, with some media outlets sensationalizing the initial risk assessment, while others disregarded the story entirely until after the safe flyby was confirmed. Part of this communication challenge originates from the inherent uncertainty in early orbital determinations. When an asteroid is initially discovered, its trajectory remains poorly constrained due to limited observational data. The uncertainty region, the range of possible orbits, consistent with available measurements, can encompass both impact and miss scenarios. Only additional observations can narrow this uncertainty sufficiently to make definitive predictions. This generates a fundamental tension in planetary defense communication. Waiting until impact probability reaches zero means potentially sacrificing valuable preparation time if the object does prove to be on a collision course. Yet releasing information while significant uncertainty persists risks triggering unnecessary panic or, worse, public skepticism if the threat assessment changes as improved data becomes available. The September wave also emphasized gaps that persist in our detection capabilities despite recent advances. Long-period comets arriving from the outer solar system can still materialize with relatively minimal warning, as their highly elliptical orbits spend the majority of their time in the distant reaches where they remain undetectable. Comet Swift-Tuttle, for instance, won't return to the inner solar system until 2126. Yet its nucleus is estimated at 26 kilometers in diameter, large enough to cause global devastation if its orbit were to intersect Earth's trajectory. Perhaps most troubling are the city-killer-sized objects in the 100 to 300 meter range, large enough to cause regional devastation, yet small enough to remain difficult to detect until they're very near to Earth. Current surveys have cataloged most of the kilometer-plus objects capable of causing global effects, yet the inventory of smaller potentially hazardous asteroids remains incomplete. The September events also raised uncomfortable questions about our ability to manage multiple simultaneous threats. While FA-22 dominated headlines, dozens of smaller objects were simultaneously threading their way through our local cosmic vicinity. If several city-killer-sized asteroids were approaching simultaneously from different directions, would our tracking and characterization capabilities become overwhelmed? Could we mount deflection missions against multiple targets using current technology and resources? These scenarios remain hypothetical, yet they underscore the importance of continued investment in planetary defense infrastructure. The completion of the Rubin Observatory survey, the deployment of NEO Surveyor, and the ongoing development of deflection technologies represent crucial steps toward a genuinely robust planetary defense capability. Yet they also represent merely the beginning of what will constitute a multi-generational effort to safeguard human civilization against cosmic impacts. The encouraging news is that planetary defense fundamentally represents a solvable problem. Unlike earthquakes, volcanic eruptions, or other natural catastrophes, asteroid impacts can be prevented entirely with sufficient advanced warning and appropriate technology. The physics of deflection are well understood. The necessary technologies exist within our current capabilities. and the international cooperation framework already exists. What we require now is the political commitment to maintain funding and support for these systems during the extended intervals between major impact threats. Planetary defense resembles insurance. It seems unnecessary right up until the moment you desperately require it. The September wave served as a valuable reminder that we inhabit an active cosmic environment where impacts are not a matter of if but when. Yet, as astronomers worked to catalog and characterize the parade of near-Earth objects during those eventful autumn weeks, a different type of mystery was beginning to emerge from the observational data. The timing of the encounters, the clustering of trajectories, and the remarkable coincidence of an interstellar visitor arriving during the same narrow time frame was starting to strain the boundaries of statistical probability. Were we witnessing an extraordinarily unlikely convergence of unrelated events? Or was something more fundamental orchestrating this cosmic choreography? The human brain is exquisitely designed to detect patterns even when none exist. This evolutionary adaptation assisted our ancestors in identifying predators concealed in tall grass and recognizing seasonal changes that meant the difference between abundance and famine. Yet in the context of astronomical phenomena, this same pattern recognition system can mislead us, finding connections and conspiracies in the random noise of cosmic events. Nevertheless, sometimes the patterns are genuine. Consider the timeline. Asteroid 2025 FA22 sweeps past Earth on September 18th at 2.2 lunar distances. 3 days earlier, smaller object 2025 RAJ2 passes at just 0.78 lunar distances. Throughout the same week, multiple additional near-Earth objects thread their way through our local cosmic neighborhood, each one cataloged and monitored by global surveillance networks. Comet C 2025 R2 brightens toward naked-eye visibility in the evening sky. And lurking in the background, interstellar visitor 3I Atlas approaches its October perihelion after a journey that may have spanned billions of years. Taken individually, none of these events proves particularly remarkable. Dozens of asteroids pass within 0.05 astronomical units of Earth every month, following orbital mechanics established billions of years ago. Comets regularly brighten and fade as they approach and recede from the Sun. Interstellar objects, while rare, represent expected consequences of planetary formation and evolution around other stars. Yet the clustering of these events within such a narrow temporal window begins to challenge simple explanations based on cosmic coincidence. What are the probabilities that an interstellar visitor would arrive during the same month as an unusually active period of near-Earth object encounters? How probable is it that a newly discovered comet would reach peak visibility precisely as multiple asteroids are making close approaches? One speculative thread worth examining involves gravitational shepherding, the possibility that 3I, Atlas's passage through the inner solar system, could somehow influence the trajectories of smaller objects. Large bodies can gravitationally perturb the orbits of smaller ones, potentially generating a debris stream or entourage effect that might explain the clustering of September encounters. However, the physics argue strongly against this scenario. 3I Atlas, even at its maximum estimated size of approximately 6 kilometers, carries insufficient mass to gravitationally influence objects at distances of millions of kilometers. Newton's inverse square law means that gravitational effects diminish rapidly with distance, becoming negligible at the scales involved in the September encounters. Moreover, the orbital elements of the various September visitors show no evidence of common origin or shared dynamical history. FA22 follows a typical near-Earth object orbit with modest eccentricity and inclination. The smaller asteroids detected throughout the month display the full range of orbital characteristics expected from the background near-Earth object population. None exhibit the hyperbolic trajectories that would indicate recent gravitational Interaction with an interstellar intruder. A more plausible explanation for the apparent clustering involves observational bias and detection cadence effects. The Vera C. Rubin Observatory had just achieved first light in June 2025, dramatically expanding our ability to detect and track small near-Earth objects. Improved survey coverage naturally leads to more discoveries, creating the impression of increased activity, even when the underlying population remains constant. Consider it analogous to suddenly installing high-definition security cameras in a previously unmonitored area. The number of people walking through the space hasn't changed, but your awareness of their presence increases dramatically. Similarly, enhanced astronomical surveys reveal the true density of near-Earth. Objects that were always present but simply went undetected by less sensitive instruments. The psychological phenomenon of apophenia, the tendency to perceive meaningful patterns in random information, may also be influencing our interpretation of the September events. Once the first few close approaches were reported, both astronomers and the public became hyper-aware of subsequent discoveries. Objects that might have passed unnoticed during a quieter news cycle suddenly received front-page treatment, creating a feedback loop that amplified the perception of unusual activity, yet even accounting for observational bias and psychological effects. Some aspects of the September wave remain difficult to explain through purely random processes. The discovery of 3I Atlas on July 1st, with its trajectory precisely timed to reach maximum visibility just as near-Earth object activity peaked, represents a remarkable coincidence that stretches the boundaries of statistical probability. Consider an alternative speculative scenario. Could 3I Atlas be not a single isolated object, but rather the largest member of a disaggregated cluster of interstellar material? If the original parent body had fragmented during its long journey through space, perhaps due to internal stresses or collisions with interstellar dust, the resulting debris stream might be distributed across a considerable volume of space. In this scenario, the September asteroid encounters might represent smaller fragments of the same original object, following slightly different trajectories that bring them into Earth's vicinity at staggered intervals. The fragments would retain their interstellar velocity characteristics, but could have been gravitationally captured into temporary solar orbits during previous passages through the inner solar system. However, this fragmentation hypothesis faces significant observational challenges. Spectroscopic analysis of the September asteroids shows typical carbonaceous or silicate compositions consistent with solar system origins. Their reflectance spectra, where available, match known asteroid taxonomic classes rather than the unusual chemistry displayed by 3I Atlas. If these objects shared a common interstellar origin, we would expect to observe similar chemical signatures across the entire population. Furthermore, the orbital dynamics don't support a common origin scenario. True interstellar fragments would display hyperbolic orbits similar to 3I Atlas itself, not the elliptical trajectories characteristic of gravitationally bound solar system objects. The energy requirements for capturing interstellar debris into stable, near-Earth object orbits exceed what's available through gravitational interactions with the planets. Perhaps the most mundane explanation is also the most likely. We're witnessing the statistical equivalent of multiple lightning strikes, improbable individual events that occasionally cluster together through pure chance. The universe contains no obligation to distribute cosmic encounters evenly across human timescales. Random processes can and do produce apparent patterns that seem meaningful to pattern-seeking intelligence. The rapid expansion of survey capabilities in the mid-2020s means we're observing this cosmic neighborhood with unprecedented sensitivity and frequency. Previous generations of astronomers might have missed most of the September encounters entirely, or detected them as isolated events spread across different news cycles. Our current ability to discover, track, and characterize multiple near-Earth objects simultaneously creates opportunities for apparent clustering that didn't exist during earlier epochs of astronomical observation. Yet, even as rational analysis argues for coincidence and observational bias, the nagging sense of orchestrated timing persists. 3I Atlas's precise arrival during a period of enhanced near-Earth object activity, combined with its unprecedented chemical signatures and ancient origins, suggests that we may be witnessing something more significant than a random convergence of unrelated events. The answer may not emerge until we've had months to study 3I Atlas in detail following its December re-emergence from solar glare. Detailed spectroscopic analysis, precise trajectory measurements, and careful comparison with the September asteroid population might reveal connections that aren't apparent in preliminary observations. Yet if no such connections emerge, if 3I Atlas proves to be genuinely isolated from the September encounters, then we're left with an even more intriguing possibility. Perhaps the universe is simply more active and interconnected than our Earth-centric perspective typically allows us to appreciate. Maybe what seems like an extraordinary convergence from our limited viewpoint is actually standard operating procedure. On galactic scales, the question isn't whether something is following 3I Atlas. The question is whether we're finally developing the observational capability to perceive the true complexity of the cosmic environment we've always inhabited. And if that's the case, then the September wave may be just the beginning of our education about what it means to be citizens of a galaxy where 400 billion stars are constantly exchanging material across the vast expanses of interstellar space. Yet before we can answer those larger questions, we need to understand why 3I Atlas itself is behaving so strangely. Because as autumn progressed and the interstellar visitor approached its closest encounter with the Sun, telescopes around the world were documenting activity and chemical signatures unlike anything observed in previous Comet solar system or otherwise. 3I Atlas continued its approach toward October perihelion. Telescopes around the world began documenting behaviors that challenged fundamental assumptions about comet physics and interstellar chemistry. What had initially appeared to be a relatively straightforward case of a wandering comet from another star system was revealing layers of complexity that seemed to violate established patterns of how such objects should behave. The most striking anomaly emerged from James Webb Space Telescope observations conducted throughout August and September 2025. JWST's infrared spectrographs detected a coma composition dominated by carbon dioxide to an unprecedented degree, with CO2 water ratios among the highest ever measured in any comet. This wasn't just unusual, it was borderline impossible according to conventional models of comet formation and evolution. That to understand why this chemistry is so remarkable, consider how comets typically form in planetary systems. Water ice condenses from protoplanetary disks at temperatures around 150 Kelvin, corresponding to orbital distances of approximately 2 to 3 astronomical units from Sun-like stars. This is why most solar system comets, which formed in the outer regions beyond Neptune's orbit, still contain substantial quantities of water ice mixed with other volatiles. Carbon dioxide, with its much lower condensation temperature, only becomes a major component of cometary ices at distances exceeding 10 astronomical units from the parent star, where temperatures drop below 80 Kelvin. Even then, CO typically remains a minor constituent. Compared to water ice. The extreme carbon dioxide dominance in 3I Atlas suggests either formation under conditions unlike anything in our solar system or subsequent processing that selectively depleted water while preserving CO, One possibility involves formation in the frigid outer regions of a planetary system much larger or colder than our own. If 3I Atlas condensed from a protoplanetary disk around a low-mass star, or in the distant reaches of a system with multiple giant planets, it might have formed in a zone where carbon dioxide ice was the primary volatile constituent. In such environments, water might never have condensed in significant quantities, leading to the extreme composition ratios observed by JWST. Alternatively, the object might have undergone extensive processing during its long journey through interstellar space. Cosmic ray bombardment over millions or billions of years could potentially alter surface chemistry through radiolysis, the breaking of chemical bonds by high-energy radiation. If this process preferentially removed water molecules while leaving carbon dioxide intact, it might explain the current composition without requiring exotic formation conditions. Yet the chemical anomalies didn't stop with carbon dioxide dominance. Spectroscopic observations from the Very Large Telescope in Chile revealed another puzzling feature: prominent emission lines from nickel atoms with surprisingly weak corresponding signatures from iron. This represents a significant departure from typical solar system compositions, where iron and nickel occur in roughly solar proportions, reflecting the elemental abundances of the stellar nebula from which they condense. The apparent depletion of iron relative to nickel in 3I Atlas raises fundamental questions about its formation environment or subsequent evolution. One speculative possibility involves differential processing of metallic components during the object's interstellar journey. Iron and nickel have different sublimation temperatures and chemical reactivities. So prolonged exposure to cosmic radiation or interstellar dust impacts might selectively remove iron while preserving nickel in more stable chemical forms. Another intriguing hypothesis involves the possibility that 3I Atlas formed in a stellar environment with non-solar elemental abundances. If its parent star belonged to a different galactic population, perhaps the thick disk or halo components that contain stars with unusual chemical compositions, resulting planetary debris might naturally exhibit iron to nickel ratios unlike those seen in our local cosmic neighborhood. As summer turned to autumn and the first Atlas approached its October perihelion, its tail structure became increasingly complex and visually spectacular. Ground-based observations from facilities like the Gemini Observatory documented multiple tail components with different orientations, colors, and apparent particle sizes. This multi-component structure suggested ongoing activation of different volatile reservoirs across various regions of the nucleus. The physics behind this complex tail development involves the selective sublimation of different ice species. As the comet encounters increasing solar heating, carbon dioxide begins outgassing at much greater distances from the sun than water ice, potentially creating an initial CO-dominated coma and tail structure. As the object approaches closer to perihelion, water ice activation might trigger a second phase of tail development with different optical properties and dynamical behavior. Polarimetry measurements, which analyze the polarization state of scattered sunlight from the comet's coma and tail, provided additional clues about the nature of dust particles being ejected from the nucleus. The polarization signature suggested dust grains with unusual size distributions or optical properties compared to typical solar system comets. This could indicate either different formation processes in the original protoplanetary disk or extensive modification during the long interstellar journey. One particularly intriguing aspect of 3I Atlas's behavior involved apparent episodic brightenings that seemed to occur independently of its distance from the sun. Most comets follow predictable brightening curves as they approach perihelion, with brightness increasing smoothly as a function of decreasing solar distance. Yet 3I Atlas displayed periodic flare-ups that suggested more complex internal processes. These outbursts might result from the sudden exposure of fresh volatile rich material as surface crusts are stripped away by solar heating. Many comets develop insulating mantles of dust and processed organics that suppress sublimation until thermal stresses or gas pressure ruptures these protective layers. When breakthrough occurs, the underlying pristine ices can sublime rapidly, creating dramatic temporary increases in activity. Alternatively, the episodic behavior might reflect internal structural changes as 3I Atlas adapted to solar heating after potentially billions of years in the cold emptiness of interstellar space. Temperature gradients penetrating into the nucleus could trigger subsurface sublimation that fractures internal ice deposits, exposing new surfaces to solar radiation and creating cascading activation events. The rotational behavior of 3I Atlas also appeared anomalous compared to typical solar system comets. Photometric observations, designed to measure brightness variations as the nucleus rotated, revealed either an unusually long rotation period or a complex tumbling motion that made period determination difficult. This might indicate structural modifications during its interstellar journey or simply reflect the original angular momentum state from whatever event ejected it from its parent system. Yet perhaps the most unsettling aspect of 3I Atlas's behavior was how normal it appeared in some respects, while being completely unprecedented in others. The basic physics of coma formation, tail development, and volatile sublimation followed well-understood principles. Yet the specific chemical signatures, temporal evolution, and structural properties seemed to violate every expectation based on decades of comet research. This combination of familiar and alien characteristics suggested that 3I Atlas represented something genuinely novel in astronomical experience. Not just another comet from another star system, but a window into planetary formation processes and stellar environments fundamentally different from our local cosmic neighborhood. The object was simultaneously confirming and challenging our understanding of how planetary systems evolve and what kinds of debris they can eject into the galaxy. As 3I Atlas approached its final weeks before perihelion passage and temporary disappearance behind solar glare, the accumulating observational evidence painted a picture of an object that defied easy categorization. It was clearly a comet based on its activity and spectroscopic properties. Yet its chemistry and behavior patterns matched no known class of solar system objects. Question was whether these anomalies reflected genuinely exotic physics and chemistry or simply represented the extreme end of natural variation in planetary system debris. And that question would have to wait for resolution until December, when 3I Atlas would emerge from its solar hiding place and present telescopes with their best opportunity for detailed characterization. Yet even as astronomers prepared for months of intensive observations, a different kind of speculation was beginning to emerge from the data. Because while 3I Atlas's weird behaviors could potentially be explained through exotic but natural processes, they also raised uncomfortable questions about whether we were dealing with something more than just an unusually active comet from another star system dot in the age of social media and viral conspiracy theories. It was perhaps inevitable that 3I Atlas would eventually face the question that has haunted every unusual astronomical discovery since the dawn of the space age. Could this be evidence of extraterrestrial intelligence? The object's unprecedented chemistry, complex behaviors, and remarkably convenient timing for observation had conspiracy theorists working overtime. By late September 2025. The speculation began innocently enough in academic circles, where researchers noted similarities between 3I Atlas and the controversial Object 1I Oumuamua that had sparked debates about possible artificial origins in 2017. Both were interstellar visitors, Both displayed unusual properties that challenged conventional understanding. Both arrived with trajectories that provided excellent observing opportunities for human astronomers. Yet the similarities largely ended there, and the differences were profound and telling. Unlike Oumuamua's enigmatic cigar-like shape and mysterious non-gravitational acceleration without visible outgassing, 3I Atlas behaved exactly like what it appeared to be a comet. It developed a classic coma and tail structure as it approached the Sun. Its brightness variations followed predictable patterns based on volatile sublimation. Its trajectory showed the expected gravitational deflection from solar interaction, with additional perturbations easily explained by outgassing forces. Most importantly, 3I Atlas exhibited no signs of controlled or directed motion. Its path through the solar system followed the precise, hyperbolic trajectory expected for an unbound visitor under the influence of solar gravity alone. There were no course corrections, no unexplained accelerations, no radio transmissions, no geometric shapes or artificial structures visible even under the highest resolution observations available to human telescopes. The scientific method demands extraordinary evidence for extraordinary claims, and the evidence for 3I Atlas consistently pointed toward natural phenomena, albeit natural phenomena unlike anything previously observed in our cosmic neighborhood. Every strange behavior, every unusual chemical signature, every anomalous physical property had plausible explanations rooted in well-established physics and chemistry. Consider the extreme carbon dioxide dominance that made 3I Atlas's chemistry so remarkable. While unprecedented in solar system comets, this composition could easily result from formation in the outer regions of an unusual planetary system. Stars with different masses, metallicities, or planetary architectures might naturally produce comets with chemical signatures that seem alien to observers familiar only with our local solar system's products. The apparent iron depletion relative to nickel, while puzzling, could reflect either formation in a stellar environment with non-solar elemental ratios or subsequent processing during billions of years of interstellar travel. Cosmic ray bombardment, interstellar dust impacts, and thermal cycling in the cold depths of space might selectively alter surface compositions in ways that create unusual spectroscopic signatures without requiring any artificial intervention. Even the complex multi-component tail structure and episodic brightening events had precedence in solar system comets, though admittedly at the extreme end of observed behaviors. Comet Hale-Bopp displayed multiple tail components with different compositions. Comet Holmes underwent a dramatic outburst that increased its brightness by a factor of nearly 1 million in 2007. Natural processes were clearly capable of producing the kinds of spectacular and unusual behaviors observed in 3I Atlas. The real question wasn't whether 3I Atlas could be artificial, it was why people kept asking. Part of the answer lay in the profound psychological impact of contemplating truly interstellar scales. When we observe objects from other star systems, we're confronting the possibility that intelligence might exist elsewhere in the galaxy. The human mind evolved to navigate social hierarchies and detect agency in complex environments, naturally looks for signs of purpose or intention in unexplained phenomena. This tendency becomes even stronger when dealing with objects that seem to violate our expectations or display properties that stretch the limits of conventional explanation. That 3I Atlas's unusual chemistry and convenient observing geometry triggered the same pattern recognition systems that our ancestors used to identify potential predators or allies. When faced with something unprecedented, the brain's default assumption is often that someone or something must be responsible. Yet nature routinely produces phenomena that exceed human imagination. The universe has had 13.8 billion years to experiment with physics and chemistry under conditions ranging from the interiors of massive stars to the near absolute zero temperatures of interstellar space. The fact that we occasionally encounter natural processes or objects that surprise us is not evidence of artificial origin. It's evidence that our understanding of cosmic phenomena remains fundamentally incomplete. The media landscape surrounding astronomical discoveries also tends to amplify speculation about artificial origins. Headlines reading, "Scientists Baffled by Mysterious Interstellar Visitor," generate more clicks than "Researchers Study Unusual but Natural Comet," regardless of which headline more accurately reflects the scientific consensus. This creates a feedback loop where public interest drives sensationalized coverage, which in turn feeds more speculation about exotic explanations. Social media compounds this effect by allowing unfiltered speculation to spread faster than careful scientific analysis. By the time astronomers have collected sufficient data to characterize an object's properties and rule out artificial origins, alternative theories have already achieved viral status and become resistant to correction through factual information. The historical pattern is clear and consistent. Every unusual astronomical discovery, from pulsars to fast radio bursts, has initially faced speculation about possible artificial origins. In every case, continued observation and analysis have revealed natural explanations that, while often more complex and fascinating than initially anticipated, require no involvement of extraterrestrial intelligence. This doesn't mean we should abandon the search for evidence of extraterrestrial technology. The universe almost certainly contains other intelligent civilizations, and some of them might be capable of interstellar travel or communication. Yet the detection of such civilizations will require clear, unambiguous evidence of artificial origin coherent radio signals with information content, objects displaying controlled motion inconsistent with natural forces, or structures that violate the laws of physics as we understand them. 3. I-Atlas displayed none of these characteristics. Its radio emissions, where detected, consisted entirely of natural thermal radiation and molecular line emissions typical of cometary outgassing. Its trajectory followed predictable gravitational mechanics, with perturbations easily explained by volatile sublimation. Its internal structure, as revealed by thermal modeling and photometric observations, was consistent with a loose aggregate of ice and rock held together by weak gravitational and cohesive forces. Perhaps most tellingly, 3I Atlas was behaving exactly like what we would expect from the debris of planetary formation around other stars. Theoretical models predict that every star system should eject significant quantities of small bodies during its formation and early evolution. These objects would wander through interstellar space for millions or billions of years before, occasionally encountering other stellar systems where they might be observed as interstellar visitors. Chemistry and physical properties of such objects should reflect the conditions. In their parent systems, different stellar masses, different elemental abundances, different planetary configurations, different thermal histories. An authentic sample of another star system's debris should look alien compared to solar system objects while still obeying the same fundamental laws of physics and chemistry that govern matter throughout the universe. In other words, 3I Atlas looked exactly like what it claimed to be a natural product of planetary system formation around another star, carrying chemical signatures that reflect formation conditions different from those that produced our local solar system family. The fact that it seemed strange to human observers was not evidence of artificial origin, but rather confirmation that we live in a galaxy where conditions for planetary formation vary dramatically from system to system. As 3I Atlas continued its approach toward perihelion, the accumulated evidence consistently supported natural explanations for its unusual properties. Yet that raised an even more intriguing question than whether it might be artificial. Where exactly had this ancient wanderer spent the billions of years between its ejection from whatever star system created it and its recent arrival in our cosmic neighborhood? The answer to that question would require sophisticated modeling of galactic dynamics and stellar motions across geological timescales. Yet preliminary attempts to trace 3I Atlas's trajectory backward through space and time were already yielding tantalizing clues about the object's origins and the remarkable journey that had brought it to our telescopes at precisely the right moment for detailed study. Tracing the biography of an interstellar visitor requires reconstructing a journey that may have lasted longer than Earth has existed. 3I Atlas carries within its chemistry and trajectory the fossilized record of cosmic events that unfolded billions of years ago, when our galaxy was younger and the distribution of stars and heavy elements was dramatically different from today's configuration. The first clues to the object's ancient origins emerge from kinematic analysis, mathematical modeling that attempts to trace its motion backward through space and time. Preliminary calculations by researchers at the European Southern Observatory suggest that 3I Atlas may have originated from the galactic thick disk, a population of stars that formed during the Milky Way's early evolution between 7 and 12 billion years ago. If these kinematic models prove correct, 3I Atlas would be older than our entire solar system. While correlations between comet appearances and solar phenomena sometimes emerge through random chance, these coincidences constitute statistical aberrations rather than evidence of causation. The meteor shower hypothesis presents another appealing yet fundamentally unsupported conjecture. Might 3I Atlas be trailing a debris field capable of generating remarkable meteor displays when Earth intersects the material? This notion gains preliminary credibility from the established fact that numerous annual meteor showers result from Earth encountering debris trails abandoned by comets. However, interstellar meteor streams confront fundamental physical constraints that render them virtually undetectable from Earth's perspective. The debris expelled from 3I Atlas maintains the identical hyperbolic velocity as its parent body, ensuring any particles it releases will likewise escape the solar system rather than establishing stable orbits capable of crossing Earth's trajectory. When our planet eventually reaches the region through which 3I Atlas passed, any ejected material will have dispersed across spatial volumes, so immense that particle density becomes effectively negligible. Furthermore, the extreme relative velocities characteristic of interstellar encounters indicate that any debris, particles somehow encountering Earth, would strike our atmosphere at speeds surpassing 70 kilometers per second, significantly faster than conventional solar system meteors. Such high-velocity impacts would generate brief, luminous flashes rather than the extended trails that define typical meteor showers. The fragmentation hypothesis represents yet another endeavor to uncover hidden connections between 3I Atlas and the September asteroid encounters. Could 2022 FA2 and the other near-Earth objects represent fragments separated from the interstellar visitor during some earlier passage through the inner solar system, now following independent orbits that return them to Earth's vicinity? This scenario confronts insurmountable difficulties regarding orbital mechanics and chemical composition. Authentic fragments from 3I Atlas would preserve hyperbolic trajectories and interstellar chemistry resembling the parent object. The September asteroids exhibit neither characteristic. Their elliptical orbits and typical carbonaceous or silicate compositions indicate conventional solar system origins, bearing no connection to interstellar material. Perhaps the most enduring cascade conjecture involves institutional concealment, the proposition that governmental agencies might be suppressing evidence of more dramatic effects or discoveries connected to 3I Atlas This theory exploits legitimate concerns regarding transparency in space, surveillance, and the potential for classified military ramifications of asteroid detection capabilities. Nevertheless, the reality of contemporary astronomical practice argues decisively against any large-scale concealment scenarios. The global network of professional and amateur astronomers operates according to principles of open data exchange and rapid publication of discoveries. Major observatories publish their observation schedules and target catalogs publicly. Orbital elements for newly discovered objects appear in international databases within days of confirmation. The incentive structure of academic astronomy also militates against secrecy. Career progression depends upon publishing significant discoveries in peer-reviewed journals and presenting findings at international conferences. A conspiracy to suppress information about 3.1 Atlas would necessitate coordination among thousands of researchers across dozens of nations, a logistical impossibility given the competitive nature of scientific research. More fundamentally, no credible evidence exists of hidden effects or concealed discoveries related to 3I Atlas. Every aspect of the object's behavior, chemistry, and trajectory has remained consistent with natural phenomena, albeit natural phenomena at the extreme end of previously observed parameters. Yet even as rational analysis dismisses the more spectacular cascade scenarios, one genuine what-if scenario merits serious consideration: the possibility that we are entering an era of dramatically increased interstellar visitor detection. The Vera C. Rubin Observatory's unprecedented survey capabilities, combined with improving space-based infrared telescopes and enhanced international coordination, could reveal that objects like 3I Atlas are far more common than previously suspected. Current estimates suggest that the Oort cloud and similar structures surrounding other stars should eject roughly one interstellar object per year that becomes detectable from Earth using existing survey capabilities. However, these estimates carry enormous uncertainties. Based on limited observational data from merely 3 confirmed interstellar visitors, if the actual rate proves higher, perhaps 10 or 20 detectable interstellar objects annually, the late 2020s could witness a revolution in our understanding of galactic scale material exchange. Instead of viewing interstellar visitors as rare cosmic curiosities, we might discover that our solar system is constantly immersed in debris from thousands of other planetary systems. This scenario would transform interstellar archaeology from a speculative science based on individual exotic objects to a systematic survey discipline capable of characterizing the chemical and physical properties of planetary formation across the galaxy. We could begin mapping the distribution of different stellar metallicities, volatile inventories, and planetary architectures by studying the debris streams that transport samples from distant worlds directly to our telescopes. Such a revelation would represent perhaps the most profound shift in cosmic perspective since the Copernican revolution. Instead of viewing Earth and its solar system companions as isolated products of local stellar evolution, we would recognize ourselves as participants in a galaxy-wide ecosystem where material constantly flows between stellar systems across vast distances and timescales. The September surge, viewed from this perspective, might represent not an anomalous clustering of unrelated events, but our first glimpse of the true activity level in our cosmic neighborhood. As detection capabilities improve and survey coverage expands, what currently appears unusual activity might prove standard practice for a galaxy containing 400 billion stars constantly exchanging debris through gravitational interactions and stellar encounters. But before we can evaluate these broader implications, we must survive the immediate challenge of 3I Atlas's perihelion passage and reemergence from solar glare. The object's behavior during its closest approach to the Sun would provide crucial data about interstellar comet survival and the preservation of ancient chemical signatures under extreme thermal processing. The stakes exceeded mere scientific curiosity. If 3I Atlas fragmented during perihelion, we might forfeit the opportunity to study intact interstellar material for decades or centuries, until another such visitor arrived with favorable observing geometry. However, if it survived, the December reemergence could provide the most detailed characterization of authentic extrasolar material ever achieved by human science. The cosmic choreography of late 2025 was reaching its crescendo as 3I Atlas approached its appointment with solar destiny. October 30th marked the calculated perihelion passage, the moment when this ancient wanderer would sweep closest to our sun after a journey that may have lasted longer than Earth has existed. Yet this crucial encounter would unfold hidden from human observation, obscured by the overwhelming glare of our nearest star. For astronomers worldwide, the perihelion period represented both the most scientifically valuable phase of the entire encounter and the most frustrating observational challenge. This was when maximum solar heating would drive the highest levels of volatile sublimation, potentially exposing subsurface materials that had been preserved since the object's formation billions of years ago. Chemical species that remained locked in solid form during the long interstellar journey would finally transition to vapor phase, revealing their spectroscopic signatures to any telescope capable of detecting them. However, the same solar radiation that promised to unlock 3I Atlas's deepest secrets would simultaneously render it effectively invisible from Earth. The object's trajectory carried it to within approximately 0.44 astronomical units of the Sun, roughly 60 million kilometers, closer than Mercury's orbital distance. From Earth's perspective, this placed 3I Atlas less than 10 degrees from the solar disk, buried in the twilight glow that makes precision astronomy impossible. The enforced observational hiatus created a tantalizing mystery. Would 3I Atlas survive perihelion intact, emerging in December as a single coherent object with enhanced activity driven by fresh volatile exposure? Or would thermal stresses fracture its internal structure, breaking it apart into multiple fragments that would create an expanding debris cloud visible as separate cometary objects? The survival question carried implications far beyond academic curiosity. Intact survival would suggest that interstellar objects possess sufficient structural integrity to preserve ancient chemical signatures, even when subjected to intense solar heating. Fragmentation, while spectacularly photogenic, might disperse the very materials that made 3I Atlas scientifically valuable, transforming a pristine sample from another star system into a collection of processed debris streams. Historical precedent offered little guidance. Most solar system comets that fragment during close solar approaches are fresh visitors from the Oort cloud, making their first encounter with significant solar radiation after millions of years in cold storage. 3I Atlas, by contrast, was a battle-tested survivor that had already demonstrated remarkable structural stability during its billion-year journey through interstellar space. The cosmic irony was palpable. After traveling unimaginable distances across space and time to reach our solar system, 3I Atlas would spend its most active and revealing moments hidden behind the very star that was driving its spectacular transformation. It resembled attending a concert where the featured performer disappeared behind a curtain during their most important song. But astronomical patience has its rewards. Earth's orbital motion around the Sun gradually improves viewing geometry for objects that pass close to our star. By early December, 3I Atlas would begin emerging from the solar glare into prime observing position. The object's closest approach to Earth was calculated for mid-December at a distance of approximately 1.8 astronomical units, roughly 270 million kilometers. This distance might seem vast by terrestrial standards, but it represented optimal conditions for detailed spectroscopic analysis, close enough for major telescopes to collect substantial amounts of light, far enough to avoid atmospheric interference from Earth's own thermal radiation, and positioned in the pre-dawn sky where background contamination would be minimal. The December observing window would likely represent the best opportunity to study intact interstellar material that human science might encounter for decades or centuries. Unlike One-Eye Oumuamua's brief visit and rapid departure, 3-1 Atlas's trajectory and timing would keep it within range of major observatories well into 2026, providing months of sustained observation across multiple wavelength ranges. Meanwhile, other members of the September cosmic cast were preparing for their own observational moments. Comet C 2025 R2 SWA, the discovery that had been brightening throughout autumn, faced its own survival challenge as it approached perihelion in early November. Fresh comets from the outer solar system often fragment under solar heating. But if Swan survived, it promised to provide spectacular naked-eye viewing for observers in the northern hemisphere. The comet's visibility window was narrowing as its trajectory carried it deeper into the evening twilight. But experienced comet hunters were reporting possible naked-eye detection under dark rural skies. Binoculars revealed a distinctive greenish, coma and growing tail structure, pointing away from the sun-classic signatures of active volatile sublimation. Whether this display would continue or end in catastrophic fragmentation remained to be seen. Asteroid 9942. Apophis continued its inexorable approach toward the April 2029 encounter that would bring it closer to Earth than our geostationary satellites. While still 3.5 years away, ground-based telescopes were already beginning extended characterization campaigns designed to map the asteroid's surface properties, rotation state, and internal structure before the close flyby altered these characteristics. NASA's OSIRIS-APEX spacecraft en route to rendezvous with Apophis after its Earth encounter was conducting periodic check-ins and navigation adjustments during its multi-year cruise phase. The spacecraft would arrive at Apophis in June 2029, providing close-up observations of how the gravitational interaction with Earth had modified the asteroid's physical properties. But the most dramatic enhancement to our cosmic surveillance capabilities was still ramping up operations. The Vera C. Rubin Observatory's first light images had demonstrated unprecedented ability to discover and track near-Earth objects. However, the facility was still in commissioning phase during autumn 2025. Once fully operational, Rubin would rescan the entire accessible sky every few nights, providing near real-time monitoring of cosmic traffic in our local neighborhood. This enhanced cadence would revolutionize asteroid detection and tracking, potentially revealing that the September surge was not an anomalous clustering, but rather a representative sample of the true activity level in near-Earth space. Previous surveys operating with much longer intervals between observations might have missed many objects or failed to recognize clustering patterns that would be obvious under continuous surveillance. The space-based component of our detection network was also preparing for major upgrades. NASA's Near-Earth Object Surveyor, scheduled for launch in September 2027, would deploy an infrared telescope specifically optimized for asteroid detection. Operating from a position trailing Earth in our solar orbit, NEO Surveyor would be able to detect objects approaching from the sunward direction that remained invisible to ground-based surveys. This capability would finally close the detection gap that allowed the Chelyabinsk impactor to arrive completely unnoticed in 2013. Once operational, NEO Surveyor should provide advanced warning of incoming objects, regardless of their approach direction. eliminating the solar blind spot that represents our most significant planetary defense. Vulnerability. For amateur astronomers and citizen scientists, the late 2025 period offered multiple opportunities for meaningful contributions to ongoing research. Comet Swan remained within reach of modest telescopes and even sophisticated cameras, allowing dedicated observers to document changes in tail structure, brightness variations, and possible fragmentation events. 3.1. Atlas's December reemergence would initially favor observers in the southern hemisphere, but its rapid motion across the sky would eventually bring it within range of northern observers as well. While the comet would be too faint for visual observation without substantial telescopic assistance, experienced astrophotographers could potentially capture images showing coma structure and tail development. More importantly, the coordinated observation of these multiple objects was providing valuable experience in international scientific cooperation and data sharing. The techniques and protocols developed for tracking 3I Atlas and characterizing the September surge would be directly applicable to future planetary defense scenarios involving potentially hazardous asteroids with short warning times. The observational challenges of late 2025 were also highlighting the importance of redundancy and international coordination in astronomical surveys. No single telescope or survey system could provide complete coverage of all possible approach directions and object types. Only through coordination between ground-based and space-based facilities across multiple wavelength ranges and observing cadences could we achieve comprehensive awareness of our cosmic neighborhood. As autumn progressed toward winter and 3I Atlas prepared for its hidden solar encounter, the global astronomical community was mobilizing resources for what might prove the most intensive characterization of interstellar material ever attempted. The stakes extended far beyond academic curiosity. The data collected during the December observing window could provide crucial insights into planetary formation processes, galactic chemical evolution, and the frequency of interstellar material exchange between stellar systems. But first, 3I Atlas had to survive its appointment with our star. The answer to that question would remain hidden until December, when telescopes around the world would turn toward this pre-dawn sky to discover whether ancient chemistry from another star system had endured one final test in its billion-year journey to human science. The convergence of enhanced detection capabilities, improved deflection technologies, and growing international cooperation in the late 2020s sets the stage for multiple possible futures in humanity's relationship with cosmic threats. The September surge and 3I Atlas encounter provide glimpses of what these futures might look like, ranging from triumphant mastery of our cosmic environment to sobering reminders of our continued vulnerability. In the most optimistic scenario, the technological and institutional foundations laid during the 2020s mature into a robust planetary defense ecosystem that effectively eliminates asteroid impact risks while revolutionizing our understanding of the broader galactic environment. The Vera C. Rubin Observatory's unprecedented survey capabilities, combined with space-infrared detection from NEO, Surveyor and similar systems create comprehensive awareness of incoming objects with decades or centuries of advanced warning. This extended lead time transforms deflection from desperate, last-minute interventions into routine celestial traffic management. Gentle nudges applied years in advance divert potentially hazardous objects into safe trajectories using proven kinetic impact techniques, refined through multiple dark-class missions. The process becomes so reliable and predictable that asteroid deflection joins earthquake prediction and hurricane tracking as accepted tools of natural disaster mitigation. Under this scenario, Comet Swan survives its 2025 perihelion passage and provides spectacular naked eye viewing throughout the northern hemisphere winter. inspiring a new generation of amateur astronomers and science enthusiasts. 3.1. Atlas emerges intact from its solar encounter and yields unprecedented insights into interstellar chemistry and galactic material exchange processes. The detailed characterization of 3I Atlas establishes interstellar archaeology as a major scientific discipline. Improved survey systems detect dozens of additional interstellar visitors throughout the late 2020s, each one carrying unique chemical signatures that illuminate different aspects of planetary formation around other stars. By the early 2030s, systematic comparison of interstellar debris provides the first comprehensive survey of planetary chemistry across different galactic environments. This scientific windfall drives technological development in spectroscopy, precision astrometry, and coordinated multi-telescope observations. The same capabilities prove invaluable for characterizing potentially hazardous asteroids, enabling precise determination of composition, structure, and deflection requirements well in advance of any actual threats. International cooperation flourishes under the pressure of shared cosmic challenges. The protocols developed for coordinating observations of 3I Atlas evolve into standardized procedures for handling any anomalous or threatening objects. Regular exercises and training programs maintain readiness while building confidence in global response capabilities. Public engagement with astronomy and space science reaches unprecedented levels as people worldwide follow the ongoing discoveries and characterization efforts. Educational initiatives capitalize on this interest to improve scientific literacy and rational decision-making skills across diverse populations. The combination of genuine cosmic threats and effective technological responses provides compelling evidence for the value of scientific research and international cooperation, but alternative scenarios present more challenging possibilities. The moderate pathway acknowledges that improved detection and deflection capabilities will inevitably encounter real tests as the catalog of potentially hazardous objects expands. Current surveys have identified most kilometer-plus asteroids capable of causing global catastrophe. But the inventory of city-killer-sized objects in the 100 to 300 meter range remains incomplete. Statistical projections suggest that one or more objects in this size range will eventually approach Earth with insufficient warning time for gentle deflection measures. These scenarios would require more aggressive intervention techniques, potentially including nuclear, explosive devices that carry significant technical and political risks. The first such encounter might involve an object discovered only months or weeks before potential impact, forcing rapid decisions about deflection strategies under enormous time pressure and public scrutiny. Success would validate planetary defense investments and probably trigger expanded funding for detection and deflection capabilities. Failure could result in regional devastation and fundamental questions about humanity's ability to protect itself from cosmic threats. Even partial success scenarios carry significant implications. A deflection attempt that successfully prevents global catastrophe but fails to eliminate all impact risk might scatter debris across populated areas, creating multiple smaller impact sites instead of a single large crater. Public perception of such outcomes could shift from viewing planetary defense as heroic protection toward viewing it as dangerous meddling with natural processes. Ocean impacts present particularly complex challenges for both deflection strategy and public communication. The majority of Earth's surface is covered by water, making ocean impacts statistically more likely than land impacts for randomly arriving asteroids. But tsunami generation from ocean impacts remains poorly understood, with significant uncertainties in current modeling efforts. A 200-meter asteroid striking deep ocean could potentially generate 10-meter waves that remain dangerous across entire ocean basins. Coastal cities from Boston to Barcelona could face devastating tsunami impacts hours after a mid-Atlantic collision. The warning time provided by successful detection might be sufficient for evacuation efforts, but the economic and social disruption would be enormous even without direct casualties. These scenarios highlight the importance of accurate risk communication and realistic public expectations about planetary defense capabilities. Our current technology can probably handle most threats, given sufficient advance warning. But late discovery scenarios, or unusually large objects, could overwhelm existing deflection capabilities. The worst-case scenarios, while statistically unlikely over human timescales, represent existential challenges that current technology cannot address effectively. A long-period comet from the Oort cloud could arrive with only months or years of advanced warning, carrying enough kinetic energy to threaten human civilization regardless of deflection attempts. Such objects with diameters potentially exceeding 10 kilometers would require deflection energies far beyond anything available through kinetic impact techniques. Nuclear explosive deflection might be theoretically possible, but the required technology development, international coordination, and deployment timelines could easily exceed available warning periods. These extreme scenarios serve as reminders that planetary defense provides protection against most threats, not all threats. Like earthquake-resistant building codes or hurricane tracking systems, defensive measures can dramatically reduce risks without eliminating them entirely. The goal is not perfect security, an impossible standard, but rather reasonable protection against reasonably likely threats. Population psychology and social dynamics introduce additional complications across all scenarios. Public reaction to asteroid threats depends heavily on risk communication strategies, media coverage patterns, and existing levels of trust in scientific and governmental institutions. Accurate information provided by credible sources can maintain social stability during crisis situations. Sensationalized reporting or conspiracy theories can undermine response effectiveness even when technical capabilities are adequate. The September surge provided valuable experience in managing public communication about cosmic threats, but real impact scenarios would involve much higher stakes and more intense media scrutiny. Social media amplification of both accurate information and misinformation could significantly complicate crisis management efforts. Economic implications also vary dramatically across different scenarios. Successful deflection of a major threat could generate enormous public support for continued investment in planetary defense capabilities. Failed or partially successful interventions might trigger more cautious approaches that emphasize evacuation and damage mitigation over active deflection attempts. The commercial space industry's growing involvement in asteroid-related activities introduces market dynamics that could either support or complicate planetary defense efforts. Private companies motivated by asteroid mining profits might develop characterization and rendezvous capabilities that serve dual purposes for both resource extraction and deflection missions. But commercial priorities don't always align with planetary defense needs. A potentially hazardous asteroid that also contains valuable resources might face competing claims from mining companies and deflection missions. These conflicts would require careful regulatory frameworks to balance commercial interests with public safety. Requirements. International politics represent perhaps the most unpredictable variable in future planetary defense scenarios. Current cooperation mechanisms work well during routine operations, but crisis situations involving potential impacts might trigger more competitive national responses. Countries might pursue independent deflection efforts rather than coordinating through international frameworks, potentially creating conflicting or counterproductive interventions. Technology development trajectories will also influence which scenarios become most likely. Breakthrough advances in fusion propulsion, artificial intelligence, Or materials science could dramatically expand deflection capabilities and extend effective warning times. Conversely, technological stagnation or reduced funding for space-based detection systems could leave us vulnerable to threats that current projections assume we'll be prepared to handle. Climate change and other global challenges compete for the same financial and political resources needed for planetary defense investments. Public and governmental attention has limited bandwidth, and asteroid threats that seem abstract or distant might lose priority relative to more immediate concerns like economic inequality, environmental degradation, or international conflicts, not yet the cosmic perspective provided by objects. Like 3i Atlas offers unique opportunities to transcend terrestrial divisions and focus on shared human interests. The knowledge that our planet exists within an active galactic environment filled with potential threats and opportunities could catalyze cooperation in ways that purely terrestrial challenges cannot achieve. As we stand at the threshold of potentially revolutionary improvements in our ability to monitor and manage cosmic threats, the futures that emerge will depend as much on our social and political choices as on our technological capabilities. The September surge and 3i Atlas encounter provide both inspiration and warning about what lies ahead in humanity's relationship with the broader cosmic environment. But before any of these long-term scenarios can unfold, we must first learn what 3i Atlas reveals when it reemerges from its solar hiding place in December. The chemical signatures and physical properties documented during that crucial observation window may provide our first detailed glimpse of authentic material from another star system and our first real understanding of what it means to be citizens of a galaxy where worlds constantly exchange their most precious substances across the vast distances between stars. As winter settles across the northern hemisphere and 3i Atlas prepares for its December reemergence from solar glare, we find ourselves at a remarkable inflection point in humanity's relationship with the cosmos. The events of September 2025 from 2022, Fa2's close approach to Swan's brightening display to the discovery of our third confirmed interstellar visitor have provided us with something far more valuable than scientific data or planetary defense validation. They have given us a new lens through which to view our place in the universe. For most of human history, the night sky appeared static and predictable. Stars wheeled overhead in eternal patterns. Planets wandered along predetermined paths, and the occasional comet or shooting star provided brief reminders that space was not entirely empty. This perspective fostered a sense of cosmic isolation. Earth and its inhabitants seemed like unique products of local stellar processes, fundamentally separated from the rest of this galaxy by unimaginable distances and timescales. The September surge shattered that illusion of isolation. We discovered that our solar system is not a quiet suburban neighborhood on the outskirts of cosmic activity, but rather a busy intersection where ancient travelers from distant worlds regularly pass through, carrying messages from their origins. 3i Atlas alone represents a direct physical connection to stellar processes that occurred billions of years ago, in regions of the galaxy we may never visit with spacecraft. This represents more than just a scientific revelation. It constitutes a fundamental shift in cosmic perspective comparable to the Copernican revolution or the discovery of the expanding universe. We are not isolated products of a single stellar system, but participants in galactic scale processes that have been exchanging materials and information between worlds for longer than Earth has existed. The chemical signatures preserved in 3i Atlas's ancient ice carry information about stellar nucleosynthesis rates, planetary formation conditions, and volatile chemistry in environments that existed before our sun began to shine. Every spectroscopic observation provides direct sampling of processes that shaped the galaxy during its youth. when star formation rates were higher and the distribution of heavy elements was dramatically different from today's configuration. But perhaps most importantly, the September events have demonstrated that we now possess the technological capability to recognize, study, and potentially interact with this galactic-scale system of material exchange. Assane detection networks that tracked 2022 FA2's approach and will monitor apophysis. 2029 Flyby can also identify and characterize interstellar visitors like 3I Atlas, with sufficient precision to extract detailed scientific information. We have graduated from passive observers of cosmic phenomena to active participants in interstellar archaeology. Every new survey telescope that comes online, every improved spectroscopic technique that gets developed, every international cooperation agreement that gets signed brings us closer to comprehensive understanding of our galactic neighborhood and our role within it. This transition carries profound implications that extend far beyond astronomy and planetary defense. The infrastructure required for monitoring cosmic threats and studying interstellar visitors' precision detection systems, rapid response capabilities, international coordination mechanisms provides templates for addressing other global challenges that transcend national boundaries. Climate change, pandemic response, resource management, and environmental protection all require similar combinations of scientific understanding, technological capability, and international cooperation. The lessons learned from tracking asteroids and characterizing comets could prove equally valuable for monitoring greenhouse gas concentrations, predicting disease outbreaks, or managing shared ocean and atmospheric resources. More fundamentally, the cosmic perspective fostered by awareness of interstellar visitors like 3I Atlas offers an antidote to the parochial thinking that often hampers cooperation on global issues. When we recognize that Earth exists within a dynamic galactic ecosystem where material constantly flows between stellar systems across vast distances and timescales, terrestrial divisions based on nationality, ideology, or economic system begin to seem less significant. We are all passengers on the same small planet, threading its way through a galaxy filled with ancient debris from billions of other worlds. The carbon atoms in our bodies were forged in stellar furnaces that died before the sun was born. The water we drink may have arrived via comets from the outer reaches of our solar system. The air we breathe contains elements that have traveled between stars for longer than complex life has existed on Earth. This understanding transforms environmental protection and social cooperation from abstract moral imperatives into practical necessities for cosmic citizenship. We cannot afford to waste the rare and precious conditions that allow complex chemistry and biological evolution to flourish on planetary surfaces. Nor can we afford to fragment our response capabilities through short-sighted competition when dealing with challenges that operate on galactic scales. The September surge has also highlighted how much we still don't know about our cosmic neighborhood and the processes that govern it. Current models predict that interstellar visitors should be relatively rare, perhaps one detectable object every few years under optimal observing conditions. But if 3I Atlas represents typical rather than exceptional activity levels, our estimates might be off by orders of magnitude. The Vera C. Rubin Observatory and other next-generation survey systems could reveal that dozens or hundreds of interstellar objects pass through our solar system annually, most of them too small or dark to detect with current technology. This would transform our understanding of galactic material, exchange rates, and the frequency of information transfer between stellar systems. Such discoveries would also raise profound questions about the prevalence of complex chemistry and potentially biological processes throughout the galaxy. If interstellar space is filled with organic compounds and volatile materials that originated in diverse planetary environments. Then the ingredients for life might be distributed far more widely than we currently realize. Every comet that enters our solar system, whether from the local Oort cloud or distant, interstellar space carries samples of the chemical conditions that existed during its formation. These natural laboratories provide direct access to processes and environments that remain beyond the reach of our most ambitious spacecraft missions. But studying these cosmic messengers requires continued investment in the detection, tracking, and characterization capabilities that made the September discoveries possible. The technologies and institutional frameworks that allowed used to identify 3I Atlas as an interstellar visitor and track 2022. Fa2's safe passage represent decades of scientific development and international cooperation. These capabilities are not self-maintaining. They require ongoing funding, technological upgrades, and political support from governments and institutions worldwide. The long intervals between major impact threats or spectacular interstellar visitors can make it tempting to reduce investments in planetary defense and cosmic surveillance systems. This would be a profound mistake. The September surge has shown us that our cosmic neighborhood is far more active and interconnected than we previously realized. We are finally developing the observational and analytical tools needed to understand our place within galactic-scale processes that have been operating for billions of years. The coming decades could witness revolutionary advances in our understanding of planetary formation, stellar evolution, and galactic chemical evolution based on direct sampling of interstellar materials delivered to our telescopes by natural cosmic processes. But only if we maintain and expand the capabilities that made these discoveries possible. The choice before us is clear. We can embrace our role as cosmic citizens, investing in the technologies and institutions needed to monitor and understand our galactic environment while protecting our planet from cosmic threats. Or we can retreat into terrestrial parochialism, abandoning the cosmic perspective, just as we're beginning to glimpse the true complexity and wonder of the universe we inhabit. The September surge and so 3-1 Atlas encounter argue powerfully for the first path. We have been given unprecedented opportunities to study authentic samples from other star systems while demonstrating our growing capability to protect Earth from cosmic threats. These achievements represent the beginning of humanity's transition from a planet-bound species to active participants in galactic-scale phenomena. But this transition will only succeed if we maintain the curiosity, cooperation, and commitment to scientific understanding that made it possible. The cosmos has delivered remarkable gifts to our telescopes and detection networks. Whether we prove worthy of these gifts will depend on the choices we make in the months and years ahead. As 3I Atlas prepares to re-emerge from behind the solar glare, carrying chemical signatures from another star system in another era of galactic evolution, we stand ready to receive its messages about planetary formation processes and cosmic material exchange that we could never study any other way. What we learn from this ancient wanderer may reshape our understanding of how worlds form around other stars, how life-essential materials get distributed throughout the galaxy, and what it truly means to be cosmic citizens in a universe where 400 billion stars are constantly exchanging their most precious substances across the vast distances of interstellar space. The September surge was just the beginning. The real adventure in cosmic archaeology and interstellar understanding lies ahead, waiting for us to develop the wisdom and cooperation needed to read the messages that ancient wanderers, like 3I Atlas, carry across the dark spaces between worlds.